and comments because yeah, I don't really know this WebEx system very well. So if you raise your hand, there's a big chance I won't even see it, or if you comment in the chat. So please just shout. And yeah, I think we have plenty of time to just have a discussion to clarify things. Okay. So what I want to talk about was this slightly more broad topic than what I had proposed before. I will still talk about probabilistic circuits, of course, for a good chunk of time. But I wanted to zoom out a little bit and talk about kind of the role of reasoning in AI today. And kind of approach this from this good old-fashioned AI perspective, where there's always been this dilemma between reasoning and learning. And the whole talk will really be about how to integrate this reasoning side, which is traditionally done with logic, and the modern deep learning side. Is my audio coming through okay? I hear sometimes some strange noises. I suppose it's not a problem. Looking at someone to nod. I guess things are okay.
Oh, sorry, I can't hear well.
Is the audio coming through okay? No, I guess that means no.
Not quite sure.
Well, okay, so please shout if I need to adjust any settings here. I suppose it will be okay. All right. So this is the outline for what I wanted to talk about. So I'll start with a little bit of a preliminary discussion of what it means to learn to reason from data. And we'll observe some paradox there. And maybe the conclusion will be that just deep learning itself is perhaps not sufficient to learn how to do reasoning. And then the second part will all be about probabilistic circuits or tractable deep generative models. And so there we'll investigate various ways of doing probabilistic reasoning in conjunction with deep learning. And then finally, we'll talk about how to do logical reasoning with deep learning. And so that's the agenda for today. All right. So first, this paradox of learning to reason from data. So the question we wanted to answer here is, can language models like BERT, transformers, be trained to perform logical reasoning? And kind of this is inspired by this work, mostly in the NLP community, where people try to come up with maybe harder benchmark problems that somehow require reasoning as part of building a solution. These Q&A data sets, for example, here, something from the Clutter data set where you're given a piece of text about Kristen and Justin and Carol and how they're related. And you get a question about this paragraph, how are they related? And the answer is Carol is the grandmother of Justin. And you can train a model to solve this task, but what we're kind of interested in this work is, do you actually solve this problem using logical reasoning, right? It's totally fine for many applications that this would not be the case, right? If you want to do, let's say, sentiment analysis, you're given a review, and you want to know if it's positive or negative, you probably don't need logical reasoning to actually figure this out. Just by looking at the important keywords, it's fine to get a sense of whether this is a positive or a negative review. But if you're talking to your AI doctor, maybe you want your AI doctor to actually reason its way to the answers it gives you, right? And so what do I mean with reasoning? Well, the language models currently, they just give them some input and then some magic black box stuff happens, and it might give you still the correct answer. Carol is the grandmother of Justin. And so what we are interested in this paper is figuring out whether the way that this is solved is by using logical reasoning, meaning going from the input to the next deduction, the next little step of your proof, from there going to the next step of your proof, and each step is somehow kind of self-evident given everything you know, but then you reach actually the non-trivial conclusion that Carol is the grandmother of Justin. Okay, and our goal is to figure out, is this what's happening when we learn, let's say, BERT or a language model to do reasoning. Okay, so let's try to use our standard approach for this, the one that you will often find in the literature. Let's just generate a bunch of data that we train on, and then let's see if we can actually generalize to a test set, okay? And the way that we'll do this more specifically is using this thing called simple logic. These are the examples that you train on, and they're written in English, but the English is kind of meaningless. It uses these adjectives: witty, diplomatic, careless, condemned, attractive, blushing. These are just words. We use them as kind of proxies for propositions in logic that may or may not be true. And what these rules are saying is that if this witty property holds, whatever it means, then the diplomatic property must also hold about some person else. Then we're given some basic properties of Alice, being thoughtless, polite, scared, average, condemned, sensible. And the question is Alice shy? And so really this is a pure reasoning problem where you now have to see if you can actually prove that Alice is shy based on these rules that you're given as part of your input. Okay. Here's another way to show the same thing. All right, we have these basic facts, we have the rules, and we have our queries. And certain queries, the answer will be true, in others it will be false. We just generate a ginormous amount of data of this form. We train our language models, BERTs, T5, to predict true or false. Okay. And there's a reason why we set up the problem this way. The reason why we set it up this way is that this is really the easiest way that we could train. It's essentially the easiest version of logic that we could possibly give to a language model. So why is it easy? Well, it's just propositional logic. There's no quantifiers here. We don't say everyone is fast and there is someone normal and whatever, right? So this is just propositional logic, simplest logic there is. We also make sure that there's a bounded vocabulary. So it's always the same, I want to say 50 or 60 adjectives that are used. I don't know by heart. It's always a fixed number of rules at most. The proofs that you need to construct in order to prove that Alice is bad or sad or whatever, they will never require more than 6 reasoning steps. Okay, so the proof trees are very shallow. Because we've made a finite vocabulary and a finite number of rules, the space of problems is also finite, right? So we don't have to deal with, first order logic over infinite interpretations, whatever. Like this is just a finite space. It's easy. From a natural language processing point of view, it's also easy. There's no variance. We don't have to deal with the fact that fast and speedy are synonyms, right? It's always the same. We don't have to deal with the fact that sometimes people state rules before facts and sometimes facts before rules. Doesn't matter. It's always the same template. Okay, so the NLP parsing side is trivial. It's also self-contained. You don't need to understand anything about the world to solve this. You don't need to understand that smart people are often not very fast, whatever. Whatever common sense knowledge you think you have, it's irrelevant to this logical reasoning task. Okay, and so these properties all make it much easier to solve this simple logic task than some of the other natural language processing tasks like question answering and common sense reasoning or vinaigrette schemas. Everything's purely symbolic, so there's no, the meaning of these words is irrelevant, and so therefore there's no shortcuts using the meaning of the words. It's not like if the review contains the word I returned the item or whatever, then it's a bad review, right? So that there is no meaning per se, it's just a purely symbolic activity. And then finally, perhaps most important, is that this is a tractable logic. These are all definite clauses. Proving whether the query is true or false can always be done efficiently. And so we're not here trying to train a neural network to solve some NP-hard problem. It's feasible that this could be learned. Okay? Any questions about this setup? I'm wondering if I will hear if someone asks a question. So far, I've only heard video. Okay. Well, it will be reassuring if I hear some voice.
Yeah, so there's no questions right now. So
Okay, good. All right, so let's go ahead and let's train BERT to solve this logical reasoning task. Now, it's a little bit trickier than that. We actually have to generate data, right? Because you will not find on the internet simple logic instances that we can, just take and train from. We'll have to generate our own version. And so we have to generate things that look like this. And so here I kind of took the English out of the equation. We're just looking at facts A, B, and C. B and C are known to be true, and A is false, okay? And then we have a bunch of rules which are denoted by the arrows here, saying that if B and C are true, then F must be true. This rule says that if B is true, E must be true. This one says that A and B, if they are true, then D must be true, okay? And then we also need to figure out whether E and F and all of the other facts, all of the other propositions are true or not, in order to know whether our answer to our query is yes or no, okay? So we have to essentially generate instances of this form, which is a bunch of rules, which are the arrows, and then a bunch of assignments of true and false to all of the variables here, okay? So how do we generate such data? Well, we have to randomly somehow construct it, so let's build a random simple logic generator of data so we can train. And so one way to do this is to say, let's first sample the facts. We'll choose A, B, and C to be the facts. And we also choose that B and C are true and A is false, right? We can do this at random. These were all a bunch of independent choices. And then we can choose a bunch of rules by just choosing body of the rule, what are the premises, and what does the rule entail, what's the head of the rule, okay? And from there, the only thing you have to do is actually just do forward chaining, is to execute the rules of logic to say, well, if B and C are true and I have this rule, then F must be true, so color F blue. Same for E, color blue. D misses a premise, so D is going to stay false in my data, okay? So that's just one way of generating the data. And if you do this, you can train your transformer, and not surprisingly, you'll get very good test accuracy, okay? So you'll get something 99 to 95% accuracy in predicting whether Alice is some random adjective. Okay, makes sense? Okay, Leo's nodding. Right, so this would be our standard deep learning approach to, how to learn this concept. Now, bear with me. I'm going to mention another way of doing this. So suppose I had two PhD students and one of them decided to generate the data this way, okay? The other PhD student generated the data some other way, which, is really equivalent. We still get the same data, but we're going to do it slightly differently. We're going to first choose for all of the propositions, whether they are true or false, okay? So we choose E to be true, we choose D to be false. There's no rules yet. And then all we have to do is sample randomly a bunch of rules that connect these nodes in such a way that they agree with the labels that I already gave to A, B, C, D, E, F. Okay, so now I just fill in some edges here that agree with the colors that I assigned to the nodes. Okay, this is just another choice to generate the same type of data. All right, and if I train from this data, somehow it's even better results. I get 100% test accuracy, right? So this is not training accuracy. This is actually on a test set of unseen random instances. And then I get something like 99% accuracy even for longer reasoning depths, right? So I should say that the columns here refer to how long is the proof needed to answer the question. And on this data set, yeah, very long proofs are a little bit harder to learn, but still easy to learn. In this data set, almost everything is easy to learn. Okay, and so this data set we'll call rule priority. And this one will be called label priority. Okay. So now back to our initial question: has BERT learned to reason from data? I don't know if anyone wants to chime in with an answer here. Have we solved the task?
As per my understanding, is still the statistical relationship they learned either in the rule-based or priority-based. But yeah, we can say somehow that output is so good that we can say that it's learned to reason from data, but still not sure that it's really learning or is the better statistical relationship.
Yeah, yeah. Yeah, I think that's going to be perhaps the conclusion, that yeah, somehow from this 100%, if you can actually correctly say what proofs of depth 6 look like in what the answer should be, then it seems like it has learned something, even though it's still a statistical model, right? So it's kind of subjective how you interpret this, but there's a ton of evidence actually to say that yes, BERT has learned to reason from data. Let me just enumerate the evidence for you so that let's pretend.
Can I ask a question?
Uh-huh.
What about trying to make a system explicitly learn the logical rules, like for example modus ponens or those kind of things, as opposed to these fixed patterns of reasoning?
Yeah. Yeah, so I agree. So this is an interesting direction. You can train a kind of hybrid architecture, something neurosymbolic perhaps, and I will get to that later. You can actually put your knowledge of how to do modus ponens into the architecture of the neural network, or you can have an algorithm, a set solver where you learn with neural networks part of the problem. So that's all interesting, but that's not the goal of what you try to do here. The goal of what you try to do here is say, we're training all these models just end to end without doing this extra work. And we're training them perhaps for problems that we think require some reasoning. I don't want my chatbot for mental health advice to just give me knee-jerk reactions. I want this chatbot to actually reason about what it's saying, right? And so we're really testing that ability. And then, of course, if that ability ends up not being there, then we can think about, baking some reasoning into the actual neural network. Make sense?
Okay.
Okay, nice. Okay, so why is this clearly doing reasoning? Well, it's very easy to actually learn this problem, right? I mentioned all the reasons before. There's no logical or computational complexity excuse here, right? It's totally feasible that this could be learned. Both of these data sets, they actually cover the entire problem space, right? They really try to generate all possible types of instances, and they generate the same possible types of instances. So there's no issue here per se with going out of distribution, in the sense that MNIST digits look a certain way. They never look entirely white. They're mostly black images. But here we're really generating all possible random images. Not images, but logic problems. We have 100% test accuracy, almost. If it's not 100, then it's 99%, right? So that's a big piece of evidence. And then perhaps most convincing is that Honghua, my student, actually proved by construction that you can choose some set of parameters of this BERT model that are perfect, that actually simulate logical reasoning, right? You can check the paper linked here for the details, but if you have a BERT model with n layers, then essentially you can simulate deductive proofs of any length less than n minus 2. Right? So if we just have enough layers, in this case 6 plus 2, and enough attention heads for our vocabulary, then yeah, you can actually handcraft parameters that would be doing reasoning that actually simulate modus ponens essentially. And so the only challenge here is for the neural network learner to find these parameters. Okay? And so the parameters exist. They do simulate logical reasoning because that's exactly how they were designed to encode that process. And we get 100% accuracy. So surely under these conditions, we have learned to do reasoning. Okay? And of course, I told you there was going to be a paradox. So here's the paradox. Remember that we had these two data sets that my hypothetical two PhD students generated slightly differently, and they both really got 100% accuracy almost. Well, it turns out that if you train on the one data set where you first do the rules and then the labels, and you test on the other data set where you first randomly generate labels and then rules, then the performance goes down dramatically, where at some point it becomes almost as bad as random guessing. Similarly, if you train on the model, on the data set that gave us 100% test accuracy, even for a depth of 1 or 2, the performance becomes really, really bad. Okay? And so this is weird. This is surprising. So there's really two options. Either BERT has learned to do reasoning, which is the thing that we argued for in the previous slide, but then it should never have such generalization failure. If BERT actually learned to do reasoning, then it doesn't matter how you generate your data. The reasoning function that you've learned is the same, and it's correct in either scenario, so it should be 100% everywhere. Okay? If I would take these parameters that I mentioned earlier, right, these parameters that actually compute the ground truth reasoning functions, those that exist, you would also get 100% accuracy everywhere. Okay? But that's not happening, so what's going on here? On the other hand, if BERT has not learned to do reasoning, then how is it able to get 99% test accuracy on these most difficult problems in distribution test accuracy? So this is seemingly a paradox. Okay? Any questions here? Are you sufficiently surprised that this is happening? I'm sure maybe you think this was bound to happen anyway. I'm not sure.
So
How skeptical you are in general. Go ahead.
So is it because of data set creation that we are seeing this kind of things that is can reason? And we have 100% accuracy. That means it's kind of generalizing very well, or 99% accuracy. But in this case, this kind of new situations where accuracy down to 69.2%. So how do you explain the conflict between RP and LP that there is so much big difference?
Yeah, so that's a good question. So how do we know that there is not a huge distribution shift between LP and RP?
Yeah.
So there's two answers to this. So one answer is that I could argue that they're actually not that different. You could look at various statistics and see that they're really very similar in their distribution. But I think the main takeaway message here is that for you as a human, it is impossible to know whether your data is actually in or out of distribution when you do logical reasoning. So the takeaway message here is that if you believe that this drop in accuracy is because of the fact that you're going out of distribution from the data that you trained on, then that may very well be the case. So let me first say, so it's not because of any obvious reasons, right? The function stays the same. What is the ground truth function stays the same. There's not a single instance that is generated by the one method with some probability and not by the other, right? They're all generating everything. It's just differently weighed because it's impossible to perfectly match these processes. In some sense, we've attempted to generate equivalent data sets, right? So we had made no effort to kind of secretly plug in some statistical differences. So, so imagine you've done all your possible work to make sure that the data you generate is the same as the data that maybe you would deploy the model for. And then if you then believe that this is still because of out of distribution issues, then the takeaway message should be you're not able to actually generate data to learn to reason because you don't know how to generate data that is in distribution for how your model will be used.
Yeah, makes sense.
So that's one takeaway if you believe this is because of the out of distributions. And so if you train your chatbot to give you medical advice, it will be deployed in a hospital and you will not know, even if you think the hospital's distribution of medical problems is the same as the one you trained on, it might very well not be, and you might see this disastrous effect. Okay, because apparently in reasoning there is this fragility in how the data relates to the model you learned.
Okay.
But yeah, that's a good
Makes sense.
question.
Yeah, makes sense. Thank you.
Okay, so let's spend a little bit of time zooming in on why this is happening, right? And without going into too much detail, you can easily see that there are properties of reasoning that make this happen. And there's very many of them, but let me just show you one of them. And so one of them is the monotonicity of entailment, monotonicity of classical logic, which says that you can add any rules to the hypothesis. You can, to your story that you give as your textual input, you can add more if this then that type of sentences, and it doesn't change a fact that's been proven. Okay, if something is entailed by your logic, it's still entailed if you add more rules. Okay, you cannot disprove a mathematical theorem by having more axioms. These are all different ways of saying the same thing. So this means that the more rules you're given, the more likely a predicate will be proved, right? So clearly, if you have tons of rules, there's more ways of proving something, and therefore it's more likely the answer will be yes. And you do see this in the data sets. And so here's one of these statistics where I told you they look similar for the two data sets, RP and LP, right? Here we look at, for the number of rules generated, what is the probability that the answer is yes? The more rules, the more likely you can prove the answer to be yes. Here we have yet a third different way of generating data. And so here you also see the same trend. And so yeah, you could look at these histograms and tell yourself, well, actually these two data sets are very similar, right? At least in terms of the statistic. But you can also see that if you're given more than, let's say, 80 rules, then it's a pretty good guess to just say, sure, it's probably going to be label 1. Okay? And so this is not an artifact of how the data was generated, of how maybe some mechanical Turk worker chose to label the data. No, this is inherent to logic itself. Right? This is something that will always be there in logic. It's part of the function you're actually trying to learn. Okay, so what we did here was try to get rid of this effect. Try to resample our data set so that this line is essentially flat. Okay, get rid of this statistical feature as a shortcut or a proxy for the true label. You can do this, you can look at the plot, now it looks mostly flat, and so it's now we do this for the RP data set, and so now we have RP balanced, which makes this 50% for all cases. Now if you train on RP and you test on the balanced data set, you also see that the performance goes down a lot for these longer proofs, okay? And so this is highly suggestive of the fact that the model is actually using this feature, the number of rules, as a statistical feature in order to make predictions. Because once we remove this feature of the number of rules, then performance gets much worse for these longer proofs. So at least for these longer proofs, this is evidence that the model is actually using this property in order to jump to a conclusion without actually proving the theorem. Okay? And you can, of course, try to remove all such features. If you even know what they are, you can try to rebalance your data set. But even generating this RPB data set, meaning resampling this data set to flatten this curve here, just took an enormous amount of CPU time. And it should be obvious that this number of rules is just one of so many possible features that allow you to solve this reasoning problem without actually doing reasoning, okay? At least within the distribution. And not only is there the number of rules, the number of the length of the rules, whatever. There's all these how many times does the same proposition appear in the body, in the head, etc., right? So there's all these statistical features. There's then also all the joint ones, all the combinations of them, and so just removing them is essentially impossible. So you can really expect them to always be there as an artifact of the combination of generating data and properties of this reasoning function. Okay, so conclusion of this part of the talk. There is some fundamental difference between learning to do reasoning and learning to do well on these benchmarks, where you can use statistical features. And you can definitely get 100% accuracy on reasoning problems. And in fact, in the literature, you'll find tons of research papers essentially doing this, right? Generating some data that requires some reasoning, be it pure logical reasoning or set solving, or maybe something that has reasoning under the covers, like question answering or entailment or whatever. And then just test on a test set and conclude that they've learned to do reasoning, right? And so the main takeaway of this work here is to say that that's different. That's maybe also useful in many applications to do the second thing, but the first thing is a different thing altogether. And solving the second bullet here does not mean you've solved the first bullet. And so that mostly means that you have to be very careful when you deploy AI applications where this difference actually matters, right? I would like my medical doctor AI to be of the first type, not the second type. That's the takeaway message here. Okay. Any questions about this paradox here? Any skepticism? I'm trying to get a sense for my audience here. Are we dealing with deep learning skeptics here that love logic and they're already on board with this, or are we dealing with folks that believe transformers and language models are going to be the solution to all possible AI problems in future? Or yeah, I'm curious to hear your thoughts on this.
I'm certainly a believer of using the deep learning and then attach some other additional knowledge or the logics to that. But I believe that statistical relationships are quite important, or learning from the examples, because when I was learning mathematics, I learned a lot from examples. So I'm in that camp where I think that examples are really important, but yeah, concepts can help us in building the story together.
I see. Yeah. So you're more of a hybrid approach type of person.
Yeah, but if I have to select any one of them, I will go for the slightly the more data-based approach than the logical-based approach, because they are hard to create and yeah, it's like much more difficult also compared to the dataset creation. Or that require different kind of expertise, which I might not have.
Okay, that's a fair point. Any other thoughts from the audience?
I don't see any questions here. That's a box.
All right.
And
So
what do you believe in that case, that how we can supplement the statistical relationship with the reasoning part? What's your kind of the idea in that case, that in which field you lie?
good question. So yeah, the rest of this talk will really be about how to do reasoning, how to make it into the model. So I hope that will answer that question.
Yeah, great. Yeah, waiting for that.
Yeah.
Just sorry, before you move into the second part, have you tried to do something similar? I mean, not with classical logic, but something with common sense reasoning. I mean, a typical example. I mean, Tweety is a bird. Does Tweety fly? It's not abnormal. I mean, things like that. I mean, that is something that we have to be thinking first.
Yeah, good question. So we haven't really done anything else but this. And the reason why we did this very, very simple thing is because, of course, our goal was to show the limitation And the strongest way to show limitation is by showing that it fails to do the simplest possible thing, right? So as soon as we go to some non-monotonic logics, we go to first order, higher order logics, as soon as we require some common sense background knowledge, as soon as we require understanding of actual natural language as part of a problem, we're just making the problem harder, right?
Yeah,
And
of
so
course.
then the conclusion that it fails would be a weaker conclusion. So that's why we stuck to the simplest possible case.
Yeah, but I'm sorry, I just was thinking about a very simple, situation where if tweet is a bird and it's and not abnormal, then it flies. Then you don't say anything about abnormality. It's relatively simple.
Right. So you would want to, instead of like a normal deduction, you would like to do some kind of
Right.
non-monotonic logic.
Negation by failure.
Yeah,
Negation of
of course, the monotonicity property wouldn't hold anymore, but there would be other properties that tell you how likely it is that the answer is yes or no. That should also be leading to a paradox. Yeah.
Yeah, it would be interesting to
Yeah.
see.
But it would be great to see that actually proven in an experiment. Yeah. So we didn't go to that extent yet. All right. Okay, so now that you maybe believe that just learning everything from the data is not the solution, let's try to build some approaches to AI, some architectures that combine deep learning with either probabilistic reasoning or logical reasoning. And so those are the next parts of the talk. And I think I won't finish the second part, I guess, before we take a break. But we can take a break somewhere halfway through and then see where it goes. Okay. So switching gears a little bit, I would like to now focus on not logical reasoning, but probabilistic reasoning, because we actually have some pretty good architectures for doing probabilistic reasoning. And it will turn out later in the talk that when you want neural networks to do logical reasoning, they will also have to be able to do probabilistic reasoning, because the two are somehow tied together. Okay, so the goal of this work here is to kind of make sense of different neural network architectures, or even more classic models in AI, for representing a probability distribution and to reason about it. And so here's a whole bunch of things that you might have heard of, things like Bayesian networks, naive Bayes. There's a bunch of terms you've probably never heard of that are very niche, such as ESDDs, gut set networks. And then there's kind of deep generative models, what they're called, GANs. I've definitely heard of GANs. They were a big hype until recently. Variational autoencoders, and so on and so on. And these are all different ways for learning a model that gives you a joint probability distribution over very many random variables. For example, the pixels in your image, or the words in your sentence. Okay. And the key distinction I would like to draw is that a lot of the deep generative models are what's called intractable, meaning that if you want to reason with them, if you want to compute, let's say, a marginal or a conditional probability, in general, it is going to be intractable, computationally infeasible to actually do reasoning probabilistically with these models. Some of these other models, they're actually tractable. You can use them to reason. Their ability to reason is kind of baked into their architecture. I'll show that later. And so these are the tractable models. And the goal of this part of the talk is to explain how these tractable models work. Now, the issue is that there's just so many different acronyms here in this alphabet soup. It's impossible to explain all of them. This is what a lot of them look like. But I think you can already spot a pattern here. So this is a tree-shaped Bayesian network, an arithmetic circuit, a syncretic network, a probabilistic intentional decision diagram, an AND-OR graph, a cut set network, probabilistic decision graph, weighted model counting encodings, SDDNS, BDDs, SDDs, etc. So all of these tractable probabilistic models, they can really all be understood as essentially a directed acyclic graph, a computation graph, and the syntax is very different in each of them, and so that's where the big hurdle lies. You try to make sense of all these drawings. Well, I'll tell you some simplified perspective on these things that explains how all these different neural network architectures are actually tractable for probabilistic reasoning. And so we call this probabilistic circuits. They're really kind of a unifying framework to understand all of these things. Okay, so what is a probabilistic circuit? A probabilistic circuit is, like I said, a computation graph that recursively defines distributions. A computation graph is just a fancy word for a neural network. And so a neural network has an input layer, right? And at this input layer, we have input units here. These are the neurons at the input layer. And they can be anything really, but you have some assumptions about what you can do with them. So they represent very simple distributions, very often over a single random variable. And so this one here says the variable x, it's a random variable, but it's always set to false. With 100% probability, it's false. So that represents a logical literal saying not x. At the same time, you could have a variable x that is assumed to be a Gaussian with some mean and standard deviation, which is definitely a distribution, but it's a very simple one. And so what you assume is that at this input layer, all these very, very tiny simple distributions are all easy to deal with. If you would like to compute the probability of some value for the variable x, you can do that. Right over here, if I ask what's the probability of x is true, well, that's 0%. Here I ask what's the probability of x being 42, well, I can compute the density of my Gaussian at that point, and I can give the answer. In addition to likelihoods, the probability of a value for x, I also assume that I can compute other quantities of interest. I want to be able to do marginalization, which if you just have a single random variable and you have a normalized distribution, of course, the marginal is 1. Right? The marginal is the sum of all the probabilities over all of the possible values. Right? So they should sum to 1. You can also ask what is the most likely state of this random variable. Here it would be the value at of the mean. Here it would be false. Okay, so that's our input layer to our neural network. But then we'll actually build some intermediate layers to construct a larger architecture. Here you see a sum unit. And so what this represents is a mixture model. I'm going to say that this neuron here represents a weighted average with these parameters of the distributions represented by its inputs. So it's a mixture of two Gaussians over x1. And of course, you usually see these mixtures of Gaussians shown in this particular way. And what will be useful for the rest of this talk is you can really think of this choice between the left or the right Gaussian to be a latent variable, a variable z, that is really choosing between these modes, right? And so this is another way to write that distribution. Okay, so in my probabilistic circuit, I have my input layers. I have a sum neuron that takes a weighted average of these, let's say, Gaussians or other types of things. And then I can also take products of things. So I can also have neurons that represent products, and they are actually doing a factorization. They're really saying, in this case, that the joint distribution over x1 and x2 is independently the distribution over x1 times x2. And now, of course, you have to make a little bit of an inductive leap and say, well, from my input layer, which is all these Gaussians, I can now do any number of products of sums of products of sums and so on. And this is a probabilistic circuit.
Keith, there is a question here in the chat. I don't know if we might want to.
Oh, I don't see the chat somehow.
There's a graph neural networks, GNNs, have been widely used in relational symbolic domains. What do you think about the state of the art on the use of GNNs as a model of neurosymbolic computing? I don't know what.
Oh, that's a broad question. So yeah, GNNs are nice. I mean, I've done in the past a lot of work on statistical relational learning, of course, where label propagation was one of the one of the techniques that actually worked really well. And so I really think of graph neural networks as label propagation on steroids. Yeah, so that works well. In terms of neurosymbolic, I mean, I'll talk about neurosymbolic later, after the break. And yeah, I mean, yeah, I'm not sure if there's a very specific question in there. I'm sure you can build interesting neurosymbolic architectures with graph neural networks. On the other hand, of course, graph neural networks are also limited by what they can compute. Right? You'll be able to do actual set solving using the graph neural network, at least not exactly, or you might run into the paradox that I showed earlier. So there's also some limitations to be aware of. Yeah. Not sure if that answers your question, but maybe later when we talk about neurosymbolic, and if you have a more specific question, I'm happy to discuss more. Okay. Maybe I should figure out how to show this chat in this app. Okay. I don't even see a button for chat, so I guess it's a bit hopeless. Yeah. Okay. Well, I count on someone just shouting to tell me there's a question in the chat. So
Yes, sure. We can let you know once someone enters the question.
Okay, good.
Actually, I'm sorry.
Go ahead.
Actually, when we are trying to send you some message, it seems that I cannot send a message there. But for all the others, it's something deactivated, or
Oh, interesting.
I don't know.
Yeah, I'm in the Linux app for WebEx, and I don't see any button for chat here, so maybe they didn't implement it for Linux, because there's only me and like 3 other people using Linux, so
Okay.
maybe that's why. Okay. All right. Unless there's more questions, back to probabilistic circuits. So we're building, recall, so that what we're doing here is we're trying to build a neural network architecture that can somehow do reasoning automatically just by construction. Okay, and so here I've shown you how to build something that combines simple probability distributions into mixtures and products of other distributions, and yeah, you can build a very large neural network this way. You can, in fact, in practice, often have 10 or even 100 million of these edges in a probabilistic circuit. Now, the goal of this exercise is to do tractable probabilistic inference. So what does it mean? It means that we have some set of questions. Let's say I want to compute marginal probabilities. I want to know the probability that my what is the probability of this left-hand side of my MNIST image, ignoring the right-hand side in this large joint distribution, right? Something like this. And we would like that for any query of this form and any probabilistic circuit that we've learned, we can actually answer the query on that model in time polynomial in the size of the model. And so that would typically be the number of edges in this computation graph. And very often this polynomial will in fact be linear. And so that's what we're going for here. Okay, so let's see if we can compute a likelihood tractably, right? So now our set of queries Q is the likelihood, it's the probability of a complete assignment to all the random variables. And so here you see an assignment to the 4 variables. And so yes, I can actually compute the probability of this feature vector in my larger distribution. The way I do it is to actually compute the likelihood of these assignments in each of the input layers neurons. So essentially for this Gaussian here, I ask what is the density at 0.5, and that's going to be my likelihood. And so these are all the numbers, okay? These are, in this case, likelihood densities, but it doesn't really matter if it's a density or a probability. And then the next question is, well, if I have a mixture model between 2 Gaussians, then what is the likelihood of this feature vector under this mixture model? Well, it's the weighted average of the likelihoods of the 2 components, okay? And same for a product. If I have a factorization, the likelihood of the factorization is the product of the likelihoods of the components of the inputs of this neuron. And so I can really just evaluate in a feed-forward manner this computation graph, and now I get at my output 0.75, I get that this is actually the likelihood density of this feature vector here. So I have efficiently, in linear time, the feed-forward pass computed this likelihood. Does that make sense? Okay. Good. Now, is it just sums, products, and input distributions, and we just layer them all together? Is it as simple as this? We just build them like neural networks? Well, there's actually a little bit of a caveat here. So for computing likelihoods, what I showed you so far is sufficient. But if you would like to do more advanced type of reasoning, you'd need to do a little bit more work. And so let's look at the case of computing a marginal probability. Here we would actually have to assume something about the architecture, and I'll try to convince you that these are actually very intuitive properties to have of a probabilistic circuit. The first thing we have to assume is it's called smoothness. It already exists for more than 20 years, this notion of smoothness. And really what it's saying from a statistical point of view is that whenever we have a mixture of two distributions, those two distributions must actually have the same random variables in them. And from a statistical point of view, you wouldn't really do anything else, right? It doesn't make sense to not have this property. If I have a Gaussian mixture model of the height of people in Belgium and the US, it's always the height of people. I cannot create a mixture model of the age of people in Belgium and the height of people in the US, right? That doesn't make sense. Those are different units. They don't mix together, okay? And so smoothness is just saying only mix things together that are the same thing, okay? Decomposability says that anytime you take a product, anytime you factorize your distribution, you have to take a product over distributions that have different random variables in them. And again, from a statistical point of view, this is the only reasonable thing to do. You don't really want to multiply the probability of whatever, or the probability of the height of someone in the US with the probability of the height of someone in Belgium. Then you have height squared. It doesn't make sense, right? And yeah, so this decomposability property also just says when you factorize things, don't end up multiplying the same random variable twice. Okay, so with these two properties, we can actually try to build an algorithm to compute marginals on these neural networks to do that type of reasoning. And here's a quick example to maybe convince you that this is possible. So our goal here is to compute a marginal probability, which, again, recall, it basically means we have to sum over a bunch of probabilities for all the values of some random variable x, for all the random variables x, sorry. And so just to simplify things, let's just think of this as an integration problem, because yeah, the x could be continuous or discrete, but let's just say we're going to essentially sum over all values of x, be there finitely many or infinitely many ones. And so this is what we need to compute this integral. And the distribution that we need to compute this integral on is the one represented by this output neuron, right? So this is the input layer, this is the output layer. And now the issue is we have to take an integral of this sum unit here. But the sum unit is, of course, doing this weighted sum of its own inputs, and the integral of a sum is the sum of the integrals, right? Integration and summation commute or distribute, and so therefore I can just compute the weighted average of the integrals computed at the second to last layer of my neural network. Or in other words, I can push this integration problem down from the last layer, the output layer, to the second to last layer of my neural network. Does that make sense? Okay, so please do interrupt me.
So how do you push it? So it's like to the back propagation, or how you are pushing down integration to the input layer?
Yeah, good question. So we will not actually use backpropagation for this. I'll show you later how to actually implement it, but this is just purely mathematically pushing the mathematical operator backwards.
Like a chain reaction.
Yeah, like, like an equality, right? Where you say, if I know what the integrals are for these two guys, I know what the integral is for this guy.
Yeah, got it. Thank you.
Yeah, good question. Okay, now we have a problem, because now we have to take an integral of a product here. Okay, so our trick that we used here, where we change the order of integration and summation, it's not going to apply to this product unit here. But we have this property called decomposability, and decomposability says that this integral over x, y, z, over this joint distribution, it can be written as the integral over this product over these x, y, z's, which don't share any variables of integration. Okay? And so that means that we can really break up this integration problem. Instead of taking the integral of the product of these functions, we can take the product of their integrals, because all these functions are in some way independent. They have nothing to do with each other. They have different variables in them. Okay? And so again, my integral here at the output of the product unit can be computed as the product of the integrals of the inputs of that unit. And the integrals again decompose into easier ones. And so now that's interesting, right? I can push my integration problem backwards through the sum units, through the product units, through the sum, through the product, and I can always reach my input layer. And at my input layer, I have always assumed that the distribution is so simple that I can just compute whatever I want. Okay? And so now that means that I can actually compute this integral by pushing it all the way back to the first layer of my neural network. Now, how do you actually implement this? Well, you actually implement it in the reverse direction using dynamic programming, right? So this was a recursive algorithm, but if you want to make that practical, you actually have to evaluate the recursion in the reverse order using dynamic programming. And so this will be some forward evaluation of the circuit again. Let's make the example slightly more concrete. So we were given a value for x2 and x4, whatever that value is. And I want to compute the probability of those values, but x1 and x3 do not appear in this equation. So they need to be integrated out of the distribution. So we're going to integrate over x1 and x3. If I were to push this integration symbol all the way backwards, then for x1, I would end up computing the integral of this Gaussian over all values of x1, and that integral sums to 1. Okay? So that's why here we say the value is 1. For x2, it's slightly different. For x2, we're actually given a value. We're not integrating over all values of x2. So this here is just the likelihood of whatever value I'm given for x2. Okay? For x3, I get the integral again, which is 1, right? Because we're integrating over all possible values. We get a value for x4. Here we also get a value for x2. It's the same value, but it's a different Gaussian. So you get different likelihoods. Anyway, so here we have a value for what all our input layer neurons are doing. And then we just take products of sums. Okay? And this is how we get our marginal probability at the output of our Pro6 circuit. Make sense? Okay. So yeah, it's not that hard. In just a feed-forward pass, we can do some probabilistic reasoning about this type of neural network that we've learned. So here's an example. Right, so here we have MNIST images, and we can ask what's the probability of all these MNIST images. It's this much. It's kind of like bits, nuts. All right, it's the natural logarithm of the probability of all these things. But I can also just say, what is the probability of the lower half of all of these images, marginalizing out the top half of the image, and then I also get this probability, which is, of course, a much higher probability because it's only talking about half of the pixels. And so this is using the algorithm I just showed you to do marginal inference. Okay. All right, so we can compute likelihoods, we can compute marginals. So let's try an even harder type of question, perhaps, or a different type of question at least. Let's do what's called map inference. I would like to know, given my observations, given the lower half of my MNIST image, what is the most likely value of all of the other random variables. What's the most likely way of inpainting the top half of my image? Okay. Now, unfortunately, this is not just going to work, because remember previously we were integrating out Q when we were computing a marginal, and integration and summation, they commute, okay? But here we're optimizing over Q, and max and sum, you cannot change their order. The max of a sum is not the same as the sum of the maxes. And so that means that the trick that we used earlier to decompose integration and to push it back to the input layer, that's not actually going to work here. And so we'll have to see some other properties later to do this type of reasoning, but it's also possible. Okay. Okay. Good. So this is how these architectures look. This is how you use them. And the next question is, how do you learn them from data? Let me see how I'm doing on time. Actually, maybe now would be not a bad time to have a break. I guess, I kind of knocked you out with all this background on probabilistic circuits. So before we talk about learning them and their applications, perhaps this is a good time for a break. I see Leo nodding. So what did we do? We did the paradox of learning to reason from data. We talked about building a new architecture to do probabilistic reasoning. These are called probabilistic circuits. We talked about how you can do reasoning with them, specifically computing marginal probabilities. And the next part is really all about how do we learn them from data, what are the applications, and maybe I'll go back to reasoning a little bit at the end before we move on to the last part of the lecture. Okay, so where do these architectures come from? Right, so recall we cannot just layer things, we have to build a probabilistic circuit that has these properties of smoothness, decomposability, etc. in order to get these reasoning abilities. And so there's a very many proposals for how to build such architectures. I'll just mention a few of them, and because I won't have, so the goal here is to just give you a sense of how these things work. Don't worry if things are not super clear. I just want to kind of give an overview. One of the classical approaches is called the Dominguez architecture. This one is actually used for images, and it's saying that we take an image and we create a mixture of different ways of partitioning this image into left, right, or top down. And once you have this way of splitting your image into two pieces, you can do this recursively. You can now take this left-hand side image and split it again top down. And so you kind of recursively cut your image into smaller pieces, and then essentially using these product units to combine them together, and also using some units to kind of create mixtures of different ways of doing so. And so this is the Dominguez architecture for images. And so here you really kind of fix the architecture. In general, this would apply to any image, but then you train the parameters, of course, to fit a specific type of image. Another popular way to train these models is to actually use clustering in order to say, these examples are similar and should be in the same mixture component, and the orange ones are also similar. And so essentially inducing some units by clustering the examples and kind of sending them in the direction of one of the inputs, and then kind of recursing. The way that you get product units is by finding in your set of variables subsets that are strongly depending on each other, like these ones, and putting them together in one circuit, and then pretending that at least locally here they're independent of these blue features here. So essentially by clustering rows and by clustering columns, using their similarity or dependence, you can induce sums and products, and you can do this recursively. And so this is another general architecture that's more data-driven, that also allows you to come up with the structure of these circuits. Something that's really effective in practice is to use ideas from decision trees. Here, this is visualized. It's called a cut set network, where the sum nodes are really created by doing a case analysis. You say either A is true or A is false. And I will give a probability to those two scenarios, and then I will learn a distribution for these two special cases. So this is really giving you a decision tree for or a probability tree. But then at some point you don't have enough data left, so you learn a sparse tree-shaped Bayesian network in order to, from there, extract a probabilistic circuit. I'll give you an example of that later. There's another kind of general approach called einsum networks, and so here the idea is that these sums of products are very similar to the einsum operator that you have available in systems like PyTorch TensorFlow. And so you kind of want to model this sum of products computation using this type of einsum operator, because then you can also on the GPU scale up training of these types of models. And so einsum networks are a way to do that. So these are all kind of historically ways that people have come up with probabilistic circuits. I want to spend a little bit more time on a very recent approach to this. It's maybe a year old. And this ends up being the state of the art for training probabilistic circuits. So I'll spend a little bit more time on explaining how they work and how you get PCs from data. So this approach is called hidden Chow trees, and it's a little pipeline of steps that actually yield a probabilistic circuit that somehow ends up being even state of the art on MNIST, as we'll see later. Okay, so this is the pipeline. You start with your features or your random variables, and the first thing you do is you compute how strongly two features depend on each other. What is their mutual information, or if you wanted to give it as correlation. Okay, so this you can do. This is a standard approach, and so now you know how important it is to kind of put two variables close together in the probabilistic circuit, because they somehow have the same information in them. From this mutual information matrix, all this information about how things depend, you can actually build what's called a Chow tree, and this is a very classical probabilistic machine learning approach. Essentially, you take this adjacency matrix of how similar variables are, how strongly they depend on each other, and you extract from it a spanning tree. And that spanning tree will put variables close together that very strongly depend on each other, probabilistically. Okay, so now you get a tree. And this is an algorithm that was invented, I want to say, 50 or 60 years ago. It's a nice algorithm, Chow tree algorithm, to get essentially a tree-shaped graphical model or a Bayesian network that represents your data. But it's not really a very good distribution in terms of fitting complex data. You cannot really learn a Chow tree on ImageNet images and expect it to be very close to the actual data distribution. However, there's the standard trick that you can use in probabilistic machine learning to make your model much more expressive, which is to add latent variables, right? And what you do if you have a Markov chain, you turn it into a hidden Markov model. And so very similarly here, you take your Chow tree, saying which variables depend on each other, and you essentially add latent variables that kind of mediate this information. So what does it mean? Instead of the actual pixels being part of this tree, we now replace them by variables z, which don't really have any meaning. They're just latent. They're unknown variables. You can have very high cardinality, right? This is kind of like an embedding in a neural network. And so those variables still depend on each other in the same way that the x variables did. And based on this latent variable, we're now predicting what is the emitted probability of x, what is the actual observed data look like. Okay. So this is called a hidden Chow tree. And what's nice about this hidden Chow tree is that it's still a tree. And something that I haven't really emphasized very much so far is that if you have a tree-shaped graphical model, this is also a tractable model. If you're familiar with graphical model inference, there's simple algorithms that will compute any marginal probability in a tree-shaped Bayesian network in this case. And in fact, those algorithms, all they do is they compute sums of products of sums of products, so you can actually turn them into a probabilistic circuit. So the next step of the learning algorithm is take our hidden Chailou tree, which is, right, the edges here are chosen by the Chailou tree algorithm. The latent variables, they can have any number of states, any kind of embedding dimension for our data. And we turn this into a giant computation graph. And, again, don't worry too much about the details. I just want to give you a gist of how this works. So here's a tree-shaped Bayesian network. And we can turn it into this probabilistic circuit that's entirely equivalent to it. Let me quickly convince you perhaps that this is correct. The way that you do this is by starting at the leaves of your tree, where you say, I would like a distribution for A, but A depends on C. So let's pretend that C is equal to 0. Okay, so this little probabilistic circuit here is going to represent the distribution over A, given that C is 0, and given that C is 0, all the other variables are irrelevant. Okay, and A in this case has 2 values. So given that C is 0, with 30% probability A is false, with 70% probability A is true. So these are now these indicator variables. They're very simple input layer distributions. Now, of course, C doesn't have to be set to 0. C can also be set to 1. So you can make another copy of this little circuit for the case where C is 1. Then you can do the same for B. Right, so now already we have 4 different probabilistic circuits for all of these distributions of A and B, given C being true or false. Okay. So let's then make a probabilistic circuit that captures the joint distribution for A, B, and C all together for a particular value of D. Let's say D is equal to 0. So here we say, well, with some probability 20%, I will say that C is false, and with 80% probability, I will say that C is set to true or to 1. Okay. If C is set to 0, then A's distribution and B's distribution will be the one that I constructed earlier for the case where C equals 0. Similarly, over here, the distribution for B and A will be the one that corresponds to my earlier choice of C equals 1. So now I have a probabilistic circuit for the joint distribution of A, B, C for a particular value of D. I can do the same for D is 1, and then I can also say D is 0 or 1 with 50% probability, and now I have the circuit that I showed you in the beginning. It's a probabilistic circuit, it's smooth and decomposable, and it represents exactly the same distribution as my tree-shaped Bayesian network. And it's a bit technical, so don't worry too much, but essentially I can take now my hidden Chailou tree, which is a tree, and I can compile it into an equivalent probabilistic circuit. Why do I care about turning it into a probabilistic circuit? Well, now I have something that PyTorch or whatever that CUDA understands, right? I have essentially a neural network, and I can use all the neural network tricks there are to train this model. I can do mini-batch stochastic gradient descent on the likelihood function, or probably more effective is stochastic expectation maximization, which is another variant of the optimizer. And I can learn the parameters of this model, and now I'm done. So that's how it works. That's the whole pipeline. Any questions about this? It's an odd way of training a model, but it's a very effective way to get a very strong probabilistic circuit. Okay. Good. So let's look at an application. So the application here, this is an iClear paper from this year. The application is to do image compression. So in image compression, you take the original data, you encode it into a stream of bits, which hopefully will not be too many bits, right? You want to compress into a small amount of data. Then you want on the other side to decode that bit stream to reconstruct the data, and because we're interested in lossless compression, we want the exact image to come out on the other side. Okay. So in order to do this, you need 2 things. The first thing you need is a probabilistic model, because you're going to do something called entropy coding, which means you actually need a model that tells you how likely is every image, and depending on how likely the image is, we can use fewer bits to compress it. So the first thing you need is that distribution P of x, and this distribution really tells you what is the theoretical rate of compression. If I'm able to explain my image data using this joint distribution over the pixels very well, then I need very few bits to actually compress the image. And again, if you're familiar with entropy coding or compression, this will sound very familiar to you. Otherwise, don't worry too much. It's just a detail of this application. The second thing you need is an algorithm that's actually efficient, that can turn your data into the bit stream and the bit stream into the data. Right? So having this distribution that tells you how many bits you need, it doesn't tell you how easy it is to encode and decode into those bits. Okay. We will not just use any entropy coding technique, we'll use something called arithmetic coding. And again, this is, if you've taken your electrical engineering undergraduate courses, you probably have seen some version of this, otherwise don't worry too much. But this is roughly how entropy coding with arithmetic coding works. You're given some data. This is just a single image, right? But it's all the pixels 1 through k. And you're going to turn this image into a number, and you'll then turn that number into a binary string, and that's the number that you send over the wire to the other side. The way you do this is by taking your number line between 0 and 1 and partitioning it into pieces that are proportionate to the probability of seeing a particular value for your random variable. So for example, I will look at my first pixel, the top left pixel, let's say, of MNIST, and I will say, with some probability it is 0, with some probability it's 1, with some probability it's 2, and so on, okay? And the proportionate to that probability, I will assign a part of the number line to represent that value. So in this case, all of the numbers that I sent over the wire that are between 0.3 and 0.5 will all represent images where the first pixel is this particular value. Okay? Good. Then I move on to my second pixel, and I essentially take this number line between 0.3 and 0.5, and I further partition it proportionate to the probability of the second pixel's values given the first one. And I keep doing this until I have narrowed down this interval to a very, very specific number, and that number will be something like 0.45312998, whatever, and it will represent my entire image. Now I will turn that number into a binary number, and I send that binary number over the wire, and that's how I compress my image. Okay. Now, in order to do this, you need to be able to compute for a given image what is the number that corresponds to it. And so that means I need to know for my first pixel what's the probability that it's, what are the probabilities of all of these things, so that I know my first pixel is falling in this blue bucket here. Okay? And so that means I need to compute a bunch of marginal probabilities, in this case marginalizing out all the other pixels that are not x1. Okay, so this is roughly how you can use a probabilistic model to this arithmetic coding and get your bit string. And then also on the other side, of course, once you get the bit string, you see, is it this blue bucket, is it the green bucket, is it the orange bucket, to then decode the image and get back your original pixels. Questions? Okay, again, this is maybe not that relevant, but this is a nice application of probabilistic models. Okay, so let's do this, and moreover, let's actually use probabilistic circuits to be the distribution that we use to do the compression. And there's two conclusions here. One is that probabilistic circuits are actually really good at fitting data, surprisingly good. This hidden Shine-Lutri algorithm I just explained is quite effective. To the degree where it actually gives you state-of-the-art likelihoods on MNIST. So if you want to compress MNIST images, then learning a probabilistic circuit is actually the state-of-the-art way to achieve that compression. There's another nice thing about probabilistic circuits, which is that they're so well behaved that a lot of algorithms that you build around them will actually be fast and efficient. Specifically, I said if you want to do compression, you need to be able to compute these probabilities to know how to turn the pixels into a binary number and the binary number back into the pixels, right? That was this arithmetic coding algorithm. Well, it turns out that you can do this in time linear in the size of the probabilistic circuit and logarithmic in the number of pixels. And so this is very, very fast, much faster than other approaches to using deep generative models to do compression, so other neural compression algorithms. So here are some results for compressing MNIST images or fashion MNIST, eMNIST, and here you compare against kind of standard image compression algorithms like JPEG 2000, WebP, and so they actually need many bits per pixel. They need 3 to 4 bits per pixel to compress the image. Okay. While if you use a probabilistic circuit, for MNIST you only need 1.2 bits per pixel to compress the image. So here we have other baselines, flow models, VAE-based compression algorithms, and so they're all requiring more bits to compress the same images. Okay. And then the second point I wanted to make was that, yeah, probabilistic circuits, they're designed to be tractable models, right? So that means they can also be very fast at compression and decompression, actually an order of magnitude up to 40 times faster than other types of neural network approaches to image compression. And so that makes them much more practical as a type of compression algorithm. Okay. Question?
I have a question. So consider the generative network. They also kind of use the reparameterization trick to get from this some specific probability distribution, capture data from that, compress and decompress that. So I have trouble understanding how our probabilistic tractable circuits differ in generative adversarial network or something those like, because they have a similar kind of the pipelines to decompress and compress.
Yeah, so you can, in fact, this pipeline that I showed, this pipeline and arithmetic coding, you can use any type of probabilistic model. You can use a variational autoencoder, a normalizing flow, a Bayesian network, a naive Bayes model even. You can use any distribution to do this. Of course, the crappier the distribution, the more bits you'll need to compress your data.
Yeah.
Now, the difference with GANs is that if you want to do arithmetic coding, if you want to do any type of compression, the very least you need is the ability to compute a likelihood, or in this case, even a marginal in the latent space. So I'll skip over the details here, but essentially you need to compute something like this. Now, unfortunately, when you have a GAN, you cannot ask, given that these first 30 pixels are, these values, what is the probability that the next pixel is some value? That's a marginal or a conditional marginal query, and your GAN actually doesn't even really represent a likelihood function. So with GANs, you cannot actually do compression this way, at least not lossless compression. You need a type of you need a type of probabilistic model that supports at least some form of let's say at least likelihood. So an elbow is good enough, so you can use a variational autoencoder, you can use a normalizing flow, but if you can compute the marginals, the actual marginals, actually things are even better, and so that's what you can do with a probabilistic circuit.
Okay, so this probabilistic stuff on the column is the main differentiating factor compared to GAN, where you, based on the pixels, you can calculate the whole probability.
Right. And again, you can only really sample other images, but you cannot get these numbers out of the probabilities of things, and that's what you need to do compression.
Okay, got it. Thank you.
But yeah, good question. All right. Okay, so we said this. Okay, so you get great compression rates, and you get things to be really fast compared to existing approaches. Some folks, maybe not in this audience, I'm not sure, are really into other types of deep generative models, specifically normalizing flow models. And so here's a way where you can actually interestingly combine probabilistic circuits with normalizing flows. This is showing that you can replace the latent part of your normalizing flow with a probabilistic circuit that's much more expressive, and you also get a boost in the performance of your normalizing flow models. This is totally uninteresting if you don't know what a normalizing flow model is, so let me skip over it. But for those of you who know what that is, there are some interesting connections there. Another kind of recent work is trying to model genetic variation data using probabilistic circuits. So this is a computational biology paper. And so here, what we try to do is take genetic sequence data and compare how probabilistic circuits do, in relation to other types of models people have learned for modeling genetic sequence data. And so in computational biology, people like to visualize in these 2D density plots how, what the distribution looks like. And they do this for the principal components. So the first two principal components, the second two, the third two. And, a hidden Markov model, kind of a naive hidden Markov model trained on this data, as you can see, doesn't really fit the data very well, especially for the kind of the secondary kind of structure. It's not really getting, the less principal components right. This is pretty bad over here. People were using GANs in prior work to model DNA sequence data, but you can see that GANs are also kind of overshooting the distribution, right? They're generating all these things that are not actually in the data distribution, and they're spread out too thin. Okay. Restricted Boltzmann machines are pretty decent actually at this job, but I would like to argue that actually the probabilistic circuits that we learned from this data are very accurate actually at fitting the structure of this distribution. And so you can check the details of this paper if you're into computational biology and genetic sequence data, where probabilistic models are also very important. There's some ongoing work. You can find some early versions online of this work where we even improve much more over the hidden Chaylut-trees, where now instead of 1.2 bits per pixel, we need only 1.14. So this is definitely very much state of the art in learning distributions for MNIST, even beating intractable distributions. You can look at text data again. Probabilistic circuits do really well. So there's a lot of momentum in improving the scale and performance of learning probabilistic circuits from data. And so this is all here just to convince you that these models are expressive even though they're tractable. Not all of them, right? If you're going to learn a naive Bayes model, that's a tractable model, but it's not going to give you very good likelihoods. You're not going to train a good naive Bayes model. But if you train a probabilistic circuit among these kind of very expressive things like hidden Chaylut-trees, you will actually be able to fit the data really well. So that's the summary of this part. Okay. So I'm going to go very quickly now over some more details of how to do reasoning with probabilistic circuits, because I want to say a little bit about neurosymbolic things. I've been talking way more slowly than I had anticipated. So I want to make sure I have some time for the logical reasoning. So I'm just going to do like a whirlwind tour of other things probabilistic circuits. Okay, so bear with me. We talked earlier about this task of finding the most likely state of some random variables. And I told you that, the earlier trick we used doesn't work. Well, it turns out you need other properties like determinism, and let me skip the definitions, basically saying mixture models are over components with disjoint support. If you have this property, you can do a similar trick to what we did before with the integration to actually push the optimization task from the last layer back to the input layer of the neural network, and you can actually solve these optimization tasks on probabilistic circuits. And I'm skipping over the details here. What I would like to emphasize is that there's all of these harder questions you might want to reason about in distributions that are not just a marginal probability. And perhaps a famous one is called the KL divergence. This is measuring in some way the similarity between two distributions P and Q. And this here is the equation. And the perspective I'd like to take here in this NeurIPS paper from last year is that these types of queries are really themselves computation graphs that act on the distribution as a whole. What does that mean? Well, this definition of KL divergence, it's taking the distribution P and Q and it's computing this quotient of these two distributions. And so computing this function, this quantity, as a function of x, we can represent it by this operator of division. And suppose that we can take two probabilistic circuits P and Q, and we can generate a new circuit R that represents this number for all values of x, then we can somehow capture this operation. Suppose then that we can also compute the log element-wise for all possible worlds of this distribution and get a circuit out of this, then we've already solved this part of the problem. Suppose then we can multiply this circuit with this circuit, then we can get a representation of this quantity here for all values of x. And then the only thing left to do is integrate over all the possible values of x, and then we get our KL divergence. And this integration, you already know how to do. If we have a smooth and decomposable probabilistic circuit, then this integration can be done in just this feed-forward pass, right? I already showed you the algorithm. So the question is, can we actually do these other operations on probabilistic circuits in order to compute these more difficult types of queries? And moreover, if we can do this, we can compute a whole bunch of other things, right? Instead of KL divergence, I can now compute, for example, cross entropy, which uses the same ingredients in a slightly different way. And again, skipping over the details, just giving you a pointer to the literature, we can actually prove exactly under which conditions you can do these operations. So for example, if you want to take the log of a probabilistic circuit, then you need smoothness decomposability and some determinism property that I mentioned earlier. Then you get a new probabilistic circuit at the output, which happens to also be smooth and decomposable. Okay, and you can do this whole theoretical analysis of when is this possible, what's the algorithm, when is it impossible. And so this is kind of the summary. We know exactly when it's possible to do this efficiently, and we know when it is actually computationally infeasible to do these types of operations. Okay, but these are just very basic operations like sums, products, powers, quotients, logs, exponents. But what's more fun now is to glue these things together and figure out when can I compute things like Kullback-Leibler divergence, KL divergence. When can I compute a mutual information between two things? When can I compute Shannon entropy? When can I compute Renyi's entropy, Renyi entropy here, right? So for all of these information theoretic queries, we can now say when can we compute them on a probabilistic circuit and when is it intractable. And so this is just to give you a sense that there's just much more than marginal probabilities that you may want to reason about, and probabilistic circuits give you a nice framework to do so. I will skip over this part. This is about solving a marginal map, which is similar to the map problem we saw earlier, but it's kind of a combination of doing marginalization for some of the variables and optimization for other variables. And this is a very hard task, and so we recently proposed a new way of doing this by actually doing structural operations on the probabilistic circuit inside of a search algorithm. So let me skip over this. Maybe some applications are more interesting for you now because there's already a lot of technical background so far. Something fun you can do is actually build an explainable AI system around this. I think you have other lectures on explainable AI. So people try to use logic to explain why a classifier does what it does. And so the neat thing you can do with probabilistic circuits is to actually use probability to explain why a classifier does what it does. And so here's an example. We're given this image 5. And an explanation now, it's called a probabilistic sufficient explanation. It's a subset of all of the pixels, of all of the features, that is probabilistically sufficient. What does it mean? It means that under the feature distribution, it's not necessarily logically true that these white and black pixels, ignoring the gray ones, must predict a 5, right? The classifier doesn't guarantee that logically. However, in the distribution with very, very high probability, you will get that this is classified as a 5. Okay, and so that's different from logical explanation. In logical explanations, often you need to see a lot of pixels before you're absolutely certain that something is a 5. Here you can be 99.99% certain that in the data distribution this is a 5 just by looking at these white and black pixels, ignoring the gray ones. Okay, and so you get much simpler explanations of why a classifier says that this is a 5. This is another explanation. This is an explanation for a classifier doing something, and I don't know if you recognize which digit this is. Right, it looks like a 3 to me, right? The white pixels kind of form a 3, and the black pixels basically say this is not a 5 or some other digit. Well, this is kind of funny because this digit is actually a 5, but it was misclassified by the classifier as a 3. And so these white pixels here and the few black ones, they're actually sufficient for this classifier to conclude that the image is a 3, even though we can all agree it's a 5. Okay, so you can start to explain why there are certain misclassifications by seeing, which pixels are sufficient to get this misclassification. Another application that we've worked on is in algorithmic fairness. So here the goal is to learn a classifier that that makes decisions, that predicts decisions, but those decisions should be independent of some sensitive attributes like race or gender or other sensitive attributes you care about. And so the goal here is to take the data which doesn't have this type of fair label, but to actually discover what is the latent variable, what is the hidden label that we don't see that actually is fair, but it also explains the data. And again, skipping over details here, you can set up a structure of a probabilistic circuit that has these fair labels, that they must be independent of the sensitive attribute by design, but also has the unfair labels that are biased from the data, as well as all of the features. You can then train this latent variable model to actually discover what are these latent fair decisions, and you get much better performance than existing methods in fairness. Okay, there's a lot of work on how to deal with missing features in classification using probabilistic circuits to account for the missingness. So that's another pointer to an application area. And then there's also work on how to combine probabilistic circuits with Stein variational inference, with Stein sampling, with kernel methods, support vector machines, how to deal with missing data in support vector regression, and so on and so on. So if you're into kernels, then there's also some fun connection there to the probabilistic circuit literature. So these slides are just here as pointers for you if this happens to be the topic that you're into. Okay, summary of this part of the talk. Tractability is a spectrum. There's likelihoods, marginals, there's optimization, there's scale divergences, and certain models are able to answer questions, and as the questions get harder, you need more assumptions on your models, but probabilistic circuits are a nice framework to make sense of all of this. Okay, maybe summary of the entire probabilistic circuit part. We have really two axes that we care about. How expressive efficient are our models, meaning how good are they at fitting data? And of course, our GANs and other deep generative models are very good at fitting data. Some of our classical probabilistic models in the literature are not very good at fitting data. Things like naive Bayes are quite poor at fitting data. The other axis we care about, though, is whether you can actually take the learned model and compute something interesting with it. And so that's the tractability side. And so GANs are the least tractable of all. They're very, very intractable. You cannot really do anything with them except for sample new data. And these classical algorithms are tractable. You can use them to do a lot of things. And so the summary here is that there's a bunch of models out there that are both tractable and very expressive, and that kind of live in this sweet spot, which is the top right corner. And moreover, if you want to understand these architectures, they're all really just variants of this general PC kind of framework. And so if you understand probabilistic circuits, you understand all of them. Okay, if you want to know more, there's a tutorial that's just about probabilistic circuits that has a lot more technical detail even. There's also an overview paper on my website if you like to read a little bit more formally definitions and theorems and examples, then you can go there to actually have some references. Okay, if you're someone who likes to learn by actually running code, you can go to this GitHub notebook here for the probabilistic-circuits.jl library. And here you can actually just see how you train this state-of-the-art and this model, and you can play with your own versions of this notebook. Okay, so that's the second part of the talk. Any questions about probabilistic circuits?
Well, I have a question not necessarily about, well, it is about probabilistic circuits, but not about the details, but about how is the competition with, let's say, neural networks? I mean, in terms of how they are being used by the community or considered by the community as a possible alternative. I mean,
yeah, that's a good question. So for context, so this is of course the community, right? So the flows, the variational autoencoders, these are the deep learning folks trying to learn distributions. I would say that until a year ago, there was no competition whatsoever. If you wanted to learn a probabilistic circuit until, let's say, a year ago, you couldn't even learn one for MNIST. That's on the full MNIST because you couldn't even, the training wouldn't finish. You would learn essentially a crappy model that has whatever 6 bits per pixel or 5 or some really bad model. Okay, so there was no competition. Probabilistic circuits were not taken seriously whatsoever. I think by people that actually cared about scaling to very large data sets with high dimensions and so on. This completely changed with kind of 2 papers, the Einsam network paper, which scaled this up using deep learning frameworks, PyTorch, etc. And then the hidden Chailutri paper, which kind of proposed this architecture that actually suddenly gets very good likelihoods that actually fits data well and scales. And so I would say that now there's a lot more interest from the wider deep generative model community to actually look at probabilistic circuits. And what's interesting is in the work that I don't present that's under review or appearing or to be submitted, things improve even much more, where things are approaching competitiveness on ImageNet 3264 data sets, where you wouldn't really expect probabilistic circuits to do well, but they're actually really quickly starting to get similar numbers to other models that are intractable. And so I would say in the last year, the interest in probabilistic circuits has grown a lot, and hopefully that momentum will keep going. Yeah. But it's all very recent, of course. Yeah, so I think people are catching up with the progress. Okay. Good. So for the last part of the talk, which I guess I'm not going to take, so I have another half hour left, I believe, right? So for this part of the talk, I would like to go back to the logical reasoning problem that we started with. And I would like to see, are there certain ways where we can do, maybe what Leo suggested is to do some neurosymbolic things where we already use some knowledge that we have and combine it with deep learning in order to actually solve some problems. And yeah, so let me get started with this. And I'll skip over this part. The main takeaway of this motivation here is that there is symbolic knowledge, even logical knowledge, in almost every machine learning application. It's just that we don't talk about it. And I'll try to convince you by giving you a ton of examples. So here's an example. This is a kind of Murphy paper. The goal is to detect players on a basketball video feed. And if you don't really do anything, you just train from data, then the model will quite often predict that there's 2 Kobe Bryants on the field, because somehow that minimizes the loss. And that's of course not what you want, so you have to add something to your model that says that people appear at most once in a frame. Okay, so this is a basic invariant, a property of the world that somehow is not learned from data, and you need to manually specify it to get your models to actually make sense. This is a paper by Leslie Kelbling about state estimation in robotics, and the issue is that if you estimate the position of these rigid objects, you will learn that they overlap, but they cannot overlap, so you have to add to your model this piece of knowledge that they cannot overlap to get reasonable predictions. Okay? If you look at the last 20 years of research by Dan Roth in natural language processing, a lot of it is about how to add knowledge about the NLP domain to your models to get them to do something reasonable. Okay? We're also working with DARPA on various applications where you need to understand a recipe. You'll cut the orange before squeezing it, and there are certain instructions and guidelines you need to follow that are given to you as knowledge that you need to train your models to actually respect. For example, if you want to do aircraft maintenance, you probably want to follow the manual. Okay. Here's another example. You try to train. You're a bank. You get customers applying for loans, and you try to train a model that predicts what loan amount people should be approved for based on their income and other features. And then if you train this model, you will actually see that there are people who would actually get a higher loan amount approved if they would make less income. And that is nonsensical. That's something that's bad for business. Possibly you'll get sued. And so this is a very basic piece of knowledge, that there is this monotonicity property that you just don't get if you learn from data. Okay. Some people only respond to DeepMind papers. So here's a DeepMind version of the same issue. So this is a kind of classic DeepMind paper. It was a big deal at the time about training a neural network, neural Turing machine type network to navigate the subway, to essentially find the shortest path in a graph. Okay, and so the goal here explicitly was for the neural network to do logical reasoning. If you train this model, there's an issue though, and the issue is it's again kind of hidden in the supplementary material at the end of the appendix on page 50 or whatever. You will find there that there's an issue. Specifically, you will find yourself at one node of the graph, and the neural network say, now go from this node to its neighboring node over here. Go from LAX to Santa Monica. But there is no edge here. You only have these two neighbors that you can move to. And so that's a problem. So what you need to do is you need to take your predictions of your neural network, and you have to essentially remove all of the predictions that are impossible. And then you're left with essentially a choice between these two neighboring nodes. Okay? And this gets worse because then at the next iteration, your neural network doesn't actually know how you fixed its predictions. So then you have to tell it, well, I didn't go from LAX to Santa Monica, I went to Hawthorne instead. So let's go from here. Okay. And yeah, so this is another example where just learning things from data does the wrong thing. It makes no sense from the physics of the world, and you have to kind of fix things outside of the system. Here's a more visual version of this. So here the input of our neural network is an image of a map of the game of Warcraft. And we need to predict how to get from the top left corner to the bottom right corner, and there's a cost for every type of surface. So this is a minimum cost path that we have to find, and the neural network has to find this solution by predicting for every edge in this map, whether it's part of the solution, part of the shortest path or not. And also here you see that things break down, so the neural network will say, oh, walk over here, and then it somehow abstains from saying how to cross this forest. But then it says, okay, finish the path here. Over here, it kind of abstains from how to cross this empty space in the middle. Over here, it doesn't really know how to cross these rocks, so it just stops here, and then it kind of bets on two possible outcomes. Right? That's interesting. It's kind of saying, my loss is minimized if I kind of give both of these partial solutions, because at least one of them will be correct. Okay. Over here, it doesn't really know how to cross this water and where to land the boat. Okay. So these are all ways in which predictions don't make sense, right? These are not paths from A to B. These are a bunch of partial predictions that makes no sense jointly. Okay, so what's going on here? So the reality is that in a lot of machine learning, we have a lot of knowledge about the world that we pretend we don't have. But we do still need it, because as I showed in all these examples, if you ignore this knowledge about the world, then things make no sense. So where does this knowledge go? Well, very often we have our Python scripts, right, that are now kind of secretly fixing everything. This is what happened in the DeepMind paper, right? Fix the things that make no sense, but kind of, shove this under the rug. In a lot of self-driving cars, you have the perception solved with deep learning, but then there's a lot of rule-based decision systems around it for safety, etc., that incorporate what we know about the world. And somehow we cannot, these are crucial, but they're not part of the learning pipeline. Often, a lot of world knowledge gets put into how we design data sets, and some of the authors of these previous papers allowed me to call what they did a big hack, where they had to solve the problem in some hacky way to kind of get the thing to work. And so this is a little bit sad. We kind of went backwards. We used to have logic in AI as a way to specify what we know, and now it's all kind of hidden underneath the surface. It's still there, but in a way that's less scientific, less principled, less pleasant to deal with. Okay. So let's see why this is happening. And so I'm going to focus a little bit on this Warcraft example. Again, feel free to ask questions about this motivation here if you disagree, especially I want to hear from you. But otherwise, let's look at this Warcraft example in a bit more detail. So what is going on here? Why is it making these mistakes? Well, let's look at what we would typically see in a research paper or at the output of our training code, which is let's look at accuracies. So here we're reporting the accuracies of a ResNet on this task of predicting the shortest path. And so let me break this down for you. So what you would normally look at is what we call the incoherent accuracy. It's how many of these edges individually are predicted to be correct, okay? And this has a very high accuracy, 97%. And of course, the reason is that this is the objective you're training for. You're just saying, predict which edges are part of the shortest path, and every edge that you get right, you get credit for. Every edge that's wrong, you get minus points for. So this is the objective. However, if you look at all of these predictions jointly for all of the edges in the graph, whether they form the shortest path, then only 56% of the predictions are valid paths from A to B. And only 44% are actually the correct shortest path. This is actually the thing that you want to predict. This is the real task, is to predict the true shortest path. And so this difference between the 44% and the 97%, that's exactly what's going on here. That's why these models fail to predict something that makes sense. Okay. So how will we try to fix this? One way that we try to fix this is by providing a tool called Pylon. This is a PyTorch framework that allows you to actually deal with this type of knowledge about your machine learning task in a very elegant way. And so the setup is very similar to what I described before. You have a neural network. It predicts some bunch of stuff jointly, like what are the edges that make up the shortest path, and then you want to essentially say that these green edges are a path from A to B. I don't know if it's the shortest one, but it's definitely something that makes sense as a prediction. Well, this prediction here is just a bunch of edges that do not form a path. This is nonsensical. This can never be a solution. So I want to essentially eliminate these bad predictions, and I only want good predictions. As I mentioned, you cannot really easily learn this from data. And so the way Pylon works is that you just write down this piece of information that we need a path from A to B. In Python, in this case, you can use a logical notation. You can just write a Python function that classifies paths as being correct or incorrect, as a concept. And you just write this constraint. And then with a minimal change to your PyTorch code, you can add this constraint to your machine learning loop. And you can train the whole thing jointly and efficiently using some magic, which I might briefly touch upon. But essentially, the Pylon library kind of takes care of making this constraint differentiable and adding it to your training loop. So in practice, it looks like this. This is your standard PyTorch code. It's a bunch of training iterations. You have your model and your existing loss, let's say across entropy. You write your function that checks whether the prediction satisfies the constraint. You add it to your loss, and this is using the Pylon API to do so. And then Pylon derives the gradient, solves everything, and trains the model. Using essentially PyTorch trains the model using this extra loss component. If you do this, things start to look much better. You get that actually there is some attempt at predicting how to cross this forest. There is some attempt at crossing this empty space. You decide to cross the rocks over here. You decide to land your boat over here. Okay, and so just adding this constraint that the predictions jointly must form a path from A to B is vastly improving the quality of these predictions. This is what the numbers look like. At a per edge basis, the accuracy kind of stays the same. However, we are now much more often predicting something that makes sense, and we're also much more often predicting the correct shortest path. And so here what we use is something called semantic loss. This is one way to turn a logical constraint into a differentiable loss function. And so yeah, this is essentially how you train the model. Okay, I'll skip over this. Let me see how I'm doing on time. Yeah, so I don't want to go too close to the end of the talk, but let me briefly tell you the magic here. So the magic that happens is we have a loss function that kind of looks like this, which is not super intuitive to read, but what it means is that we take this logical constraint, which is called alpha, and we consider all the possible predictions that the neural network could be making. And so what this here means is this is the probability that the neural network, so this is the probability according to the logics of the neural network, that the neural network will predict some x, some joint vector of probability of values, of binary values, that actually satisfies the logical constraint. So this is really the probability that, in the Warcraft example, you predict a path from A to B. You also take minus the log of this number to get a loss. So if you predict with 100% probability something that satisfies the logical constraints, then your loss will be 0. If your probability of predicting something that satisfies the constraint is very close to 0, then you will get a very large number for your loss, and so that's how you train the model. So in general, computing this quantity is sharply hard, right? Summing over all possible joint predictions, all possible paths. This is a scary thing. You don't want to do this explicitly. You can never really do this brute force. However, remember probabilistic circuits that we had earlier? You can actually do some magic where you take the logic, the logical constraint, you can turn it into a logical circuit. And skipping over some important details here, you can take your probability vector coming from the predictions of your neural network, and you can actually extract from this a probabilistic circuit that computes the probability of this constraint alpha according to the distribution at the output layer of your neural network. And you just take minus the log of this, and now you have a computation graph that is tractable, that can compute for you this big integral using these properties that we had earlier for probabilistic circuits. And so by just adding this, okay, this looks a bit different. So here we have logical gates, but you can think of these as sums and these as products. So this is really just a probabilistic circuit. So by adding this probabilistic circuit to the end of our neural network, we now have a computation graph for our loss function, which PyTorch will happily auto-diff for you and optimize. And so that's how probabilistic circuits are actually used to make logic differentiable and to do neurosymbolic learning.
May I ask a quick question?
Yeah.
So it seems, unless I'm missing something, that you can handle only propositional logical constraints, or the reason why I'm asking. The reason why I'm asking is because I mean, it's your example about basketball that you show at the beginning of this part. For me, there is something, unless I'm wrong, that that example shows some sort of common sense knowledge. for example, inertia or loss or things like that. And that
Right.
seems to be more difficult to express. I mean,
Yeah, that's a good point. So often it's more convenient to express your knowledge in another logic, right? First order logic, in non-monotonic logic, and so on. And that's fine. In fact, in Pylon, we actually allow people to write arbitrary Python code even to express the function they care about, the constraint they care about. However, the goal is, in the end, to get a differentiable loss function. As you know, if you want to do probabilistic inference with even a probabilistic database query, for very many of them, the only solution is to turn them into propositional logic and to compile a propositional circuit. So this is something that kind of always works on all types of knowledge, right? You can always turn it into propositional logic. Even if you have an answer set program, you can turn it into propositional logic, right? If you have a Prolog program, you can turn it into propositional logic. So this is really meant to be this kind of catch-all kind of lower level reasoning form. Now, of course, you can always generate your propositional logic from a higher level description. Now, as you also know, sometimes from the higher level description, you can actually do better. You can do some form of lifted inference to do this type of reasoning. But yeah, so here we're going for the general case where propositional logic is kind of the underlying thing that always works. The reason it always works, of course, is because we're always dealing with finite domains. Your neural network is not going to predict an infinite-sized interpretation. So, it's always finite, and that makes the propositional logic, fully expressive here. Does that make sense?
yeah, thanks.
Okay, good. All right. Some more pointers. The goal of this neurosymbolic learning is to essentially make sure that whatever we predict satisfies the constraint. And that's kind of visualized here. This is a density. This is saying what is the probability of every possible prediction. And then the blue area is meant to be those predictions that actually satisfy the logical constraint. And if you train a model from data, you'll have that certain non-solutions, things that violate the constraint, will have some probability. Okay. And the goal here is to really squeeze all of the probability mass into the part of the solution space that satisfies the constraint. That's exactly what Pylon attempts to do, what semantic loss as a loss function attempts to do. In some work that appeared this summer, we're actually trying to use neurosymbolic learning, or actually learn logical constraints to help with other types of supervision. Specifically learning from unlabeled data. So if you have unlabeled data, you don't really know what the right prediction is, but very often you want to say the prediction you learn has to be confident. If I'm classifying cats and dogs in images, I know that there's no other animals in my data set, so whatever you predict this unlabeled image to be, it has to be quite confidently a cat or quite confidently a dog. And this is achieved using something called entropy regularization, where you say, I want this distribution to be peaked around a very specific prediction given any particular input image. Okay. Now, unfortunately, entropy regularization doesn't work as well as you'd hope in a context where you have a lot of domain knowledge, because what entropy regularization can end up doing is very confidently predicting something that makes no sense according to the physics of the world, right? Very confidently predicting a non-path from A to B. So in this work that appeared at UAI, we actually developed something called neurosymbolic entropy regularization. And here the goal is to say, make sure you're confident in how you label data that you don't have a label for, how you classify data that you don't have a label for, but also make sure that you're only confident predicting something that satisfies my logical constraint. So put whatever peak you learn, put it in this light blue area where the constraint is satisfied. And so, yeah, you can now nicely combine these losses. Semantic loss says make the constraint more likely to be satisfied. Neurosymbolic entropy regularization says make sure that whatever you predict, you're confident about, but only within this part of the solution space that satisfies the constraint. So now you can really build this suite of neurosymbolic losses that allow you to do all sorts of machine learning using this knowledge alpha as part of the pipeline. If you do this, numbers improve even more. So yeah, it works. The way it works is again using probabilistic circuits and using this ability to do these information theoretic queries that I mentioned earlier, like entropy, because now you can also use them as a loss function. Skipping over details here. Everything I showed you so far are these kind of fun toy examples. They're very difficult to learn, but they're not really kind of real world. You're not going to use them to do a startup, right? So this slide is only here to convince you that if you actually care about practical problems, this is also, this stuff also really works. So here we try to do entity relation extraction in natural language processing. You read a paragraph and figure out what are the entities in it and how do they relate to each other. And also here you have some very basic background knowledge that if X lives in Y, then X has to be a person and Y has to be a location. Stuff like that. And if you do this neurosymbolic entropy regularization, then again, you get state-of-the-art results here for semi-supervised learning. Okay, I have 10 minutes left, so let me tell you, like, again, just rushing through pointers. Sometimes you would actually like 100% guarantee that everything is correct. And so you can check this paper, it's going to appear at NeurIPS this year, where we actually add a layer to our neural network that incorporates this probabilistic circuit that represents the logical constraint. And doing so will actually allow you to always predict something that satisfies the constraint. And so sometimes if you do semantic loss, you still make some mistakes. And the semantic probabilistic layers actually make sure that you cannot make any mistakes, in the sense you must always predict something that satisfies the constraint. This works really well in various applications, including hierarchical multi-label classification. So here you have knowledge of the form that if an image is classified as a dog, it must also be an animal. You can also have information that says if it's an animal, it must be either a cat or a dog, because you know exhaustively the classes that pertain to your data. And if you have this type of knowledge and you bake it into the final layer of your neural network as a semantic heuristic layer, then you get much better numbers on these standard hierarchical multi-label classification data sets. Okay, I'm going to skip over this part. This is some other ongoing work on how to learn the actual constraints, which gives interesting results. And then the final quick pointer I'll give before I wrap up is that, remember this monotonicity problem where the bank was giving a higher loan amount approved for people that make less money? Well, there's actually a really fun way to also do neurosymbolic learning in this application, and it's very different. It's actually using SMT solvers to find counterexamples to that are violations of this monotonicity property. Once you have these counterexamples, you can actually fix the predictions of the neural network to make them monotonic, and it actually improves performance sometimes, but it gives you mostly a hard guarantee that you will always predict something that's correct. You can also use these counterexamples, these violations of your constraint, as part of your training loop to actually improve the quality of your model. And then you can actually do both. You can fix the model during training, but also during prediction. And this actually gives you state-of-the-art results on learning monotonic functions, learning neural networks that have these monotonicity constraints. And so this is a comparison to the state-of-the-art baselines, where we do much better in these standard data sets. And so the summary is that neurosymbolic learning can sometimes give you provable guarantees of correctness, but you would think that this makes the performance worse, but in fact, very often it actually gives you state-of-the-art results, because by actually baking these invariants into your model, you're just learning much better models in the first place. Okay, so wrapping up, I hope I convinced you that this symbolic knowledge is everywhere in machine learning, and using it even a little bit vastly improves your performance. I showed this for the deep learning setting where you have structure output constraints, and I briefly just mentioned you can do something for learning monotonic neural networks, which also incorporates that piece of knowledge. And so the whole talk was about paradoxes of learning to reason, and then how to build new types of neural network architectures that can do probabilistic reasoning as well as logical reasoning about symbolic knowledge. And so that's kind of the main theme of all my research, is how to integrate reasoning into learning. And thanks for your attention, and thanks, of course, to all the folks who actually did the work developing all these techniques. Happy to take more questions if any still are out there.
Thanks a lot, Keith, for the very nice and motivating presentation. I think let's see if there are questions from the public, as opposed to the chairs. You see here a question about whether there will be some access to the slides. So it would be nice to.
Oh yeah, if you go to my website, and click on talks, the first one you'll see is are these slides already.
Okay, thanks.
No one has questions. I have a couple of questions, so I will wait for other people. Otherwise, I can ask questions, because I have came across a lot of your works where my literature research of my PhD work. So, so just to give, since you told that there are scope to implement this in the practical situations. So since you are working with the probabilistic stuff, so consider a robot moving in an environment, and a lot of uncertainty is there. And robot also work with a lot of constraints, just like you told that in the propositional logic, if something is there, please stop. So I was wanting to ask about your idea that is it feasible to include this kind of constraint, which are written in propositional logic, or say temporal logic, into a neural network? So there are 2-3 such constraints for the robot, which are probabilistic in nature, and then can use them in the planning algorithm. Is that feasible from your perspective? Do you look like?
Yeah, of course. I think it's feasible. I think there's some work from UT Austin that uses some, and also from Toronto, I suspect, using some, some LTL constraints in reinforcement learning or planning. Yeah, so I think there's actually work related to this. I myself haven't really done neurosymbolic in kind of a dynamic decision-making scenario, mostly because I feel like there's a big challenge in even making the simple classification setting work. But I think that's interesting for sure, yeah.
Yeah, because it's like since you are trying to introduce, for example, deep learning plus probabilistic. So if you see the whole area of the autonomous systems, since they operate in the situation where a lot of probabilistic stuff, that what is the intention of other traffic participant, other robot is not known. So in that case, a lot of things are taken care of by deep learning, like trajectories and all those things. So it's can be really interesting where we can combine the probabilistic with the deep learning or some kind of the logical symbolic knowledge.
Yeah.
So yeah, that's
Yeah, I
interesting.
agree. One of the challenges, of course, if you're doing some deep RL, is to do the symbol grounding, right? You need to have symbols in order to do neurosymbolic learning. There's some recent work by Chris and Kirsten also, and colleagues about how to do neurosymbolic while also doing the symbol grounding at the same time. Yeah, so there's some interesting challenges there. I think it's pretty much still open, but yeah. Good problem
Thank
to
you.
work on.